All right, so actually this is section 2.5 about enzymes. It has the wrong heading up here, but 2.5 on enzymes. Enzymes are, like we said today, they are proteins that have a very specific job in our body. They are catalysts to help promote and control chemical reactions. Now, a catalyst is anything that lowers the amount of activation energy. And remember we said today that activation energy is what's required to make a reaction occur. So a catalyst will lower that activation energy. And enzymes, as catalysts, speed up the chemical reactions because they require less activation. They make the reaction require less activation energy. And so if we're speeding up the chemical reaction because we've reduced the amount of energy required, that will increase the reaction rate of that reaction. So when you look at this picture down here, this graph, right, the solid orange line is your reaction uncatalyzed. And so you can see how much activation energy this hump, this hill that we have to get over is what we call the activation energy, or sometimes we refer to that as the transition state. But clearly we have a much greater activation energy required in your uncatalyzed reaction than we do in this dashed line, which represents the catalyzed reaction. Less energy, right? So our bodies are very regimented, they're very controlled, and so within living things we can't have major fluctuations in our internal environment. So enzymes allow these reactions to take place even though our systems are highly regulated. So our enzymes are required for just about everything that takes place in our body. Very few reactions happen spontaneously. Again, we said enzymes are proteins, right? They belong to the macromolecule category of proteins. Enzymes work really well. However, they do have parameters that they can work within. And so if the enzyme's environment is disrupted, then it's not going to work correctly. So disruptions in homeostasis, and homeostasis means kind of that natural balance that the body has so that it can keep functioning on a daily basis. So if there is a disruption in homeostasis, then the enzyme's not going to work well. And most of our enzymes have a kind of a narrow range of conditions that they can work under, right? They work best in a small range of conditions, or what we call an optimal condition. Temperature and pH are very common disruptors to an enzyme's function. And so if the body temperature is too high for too long, or if the pH, changes drastically, or not even all that drastically, but if it changes, that can cause disruptions or breaking of hydrogen bonds. And those hydrogen bonds are found within the enzyme. So an enzyme is a very complex three-dimensional protein, right? We know a protein is made when you link amino acids together. Well, that chain of amino acids gets twisted and folded and coiled up on itself, and that very specific twisting, folding, and coiling is held in place by hydrogen bonds. And so when the temperature changes or when the pH changes, those hydrogen bonds are going to break, which is then going to alter the structure of the enzyme. And the enzyme structure dictates its function. The enzyme will not work correctly if its structure has changed. And what I mean by that is if the enzyme structure because the enzyme structure is so specific, it has a very specific what we call active site. And so those active sites allow only very specific reactants to bind to it. And in enzyme catalyzed reactions, so in a chemical reaction that's controlled by an enzyme, the reactants are now referred to as substrates. So the substrate will bind, or the reactant / substrate will bind to the active site, which is a location on the enzyme. So it's like a docking station, if you will, on the enzyme. So there's my purple enzyme here. We see two active sites, one groove, one like half cylinder, and those locations are where my two substrates, the orange thing and the blue thing, are going to bind to that specific enzyme. So the blue can't bind into the active site for the orange, or vice versa. They are specific for each other. So we call that model the lock and key model, because the enzyme is the lock and the substrate is the key, and so the substrate has to fit into the enzyme like a key fits into the lock. And so that tells us that the correct substrate is being acted on by that enzyme. The enzyme also works to bring substrates together. So maybe it's an enzyme that is breaking one thing down into two, or perhaps it's an enzyme that's taking two different things and making it and putting those two different things together to make one. If that's the case, when my substrates here bind to the enzyme's job is to weaken the bonds of these two substrates, or if this was just one substrate, to weaken the bonds within it to encourage and speed up the reaction. And so once that reaction, that catalyzed reaction occurs, the new product is then released.